Our speaker tonight is Dr. Bickel. Take it away.
Well, thank you, Hunter. And this is clearly working. I want to welcome everybody. This is going to be a 7-week course, and to assure that you get here early and on time, I have laid out free artwork that you can acquire, license free. At any rate, I'm shutting down my photography business, so I've got lots of stuff that my wife is saying, we got to get that out of the garage before the squirrels get it. So at any rate, if you want to donate, I'll take some money. I could use a bottle of wine every now and then, but at any rate, it's free for the taking, and I will replace it or replenish it every week. So come early, browse before we get started each week. Before I get too far started, I usually like to start a thing like this with a few sick jokes to get everybody awake. So, where do sheep go for spring break? The Bahamas. You got it. And where do the orca whales go for summer vacation? Whales. Maybe I'll stop there before somebody says, I've heard that one before, but why did the school teacher wear shades over spring break when she went to the beach? And the answer is because her brightest students weren't around. So with that, I will begin. Okay, I'm John Bickel. Is it working now? Yeah. Got it. Thank you, Hunter. One of the things you learn in life is you can't get anything done without help from good folks. At any rate, I'm John Bickel. I'm a member of the DAS for about, since about 2019. I've lived in Colorado for the last 25 years, and I am a retired physicist, nuclear engineer. When I was in college, I spent most of my time studying about neutrons. But since I retired, I'm really looking into stars. The inside of stars, what makes them work, why they glow, why they stop glowing, and all of that. And that's been kind of my main interest in retirement. So tonight's agenda, some welcomes and introductions. I don't think we're going to be able to shake hands, but it would be nice if you turn to your neighbor and say, hi, I'm so-and-so, and I'll be seeing you for the next 7 weeks, and maybe copying each other's homework and things like that. Oh, there will be a test after. How to get the most out of this course. First of all, we are really hoping, we want you to attend all 7 sessions. They are consecutive. There was an order put into them, and I'm going to go through what we call a roadmap. The rest of my talk this evening will be what we call observable astronomical objects. Okay, first of all, this course is presented by the Denver Astronomical Society with the incredible assistance of Secular Hub. The course is going to run 7 consecutive Tuesday nights, and I think we made that clear when people were signing up that if you want to sign up, this is not a thing that you're going to do over Zoom or something like that. There will be a few short homework assignments. We will have an outdoor lab session that will be held at Chamberlain Observatory, and in the welcome letter that we sent out a few days ago, it has the address of that for the folks that have never been there. We're going to be in the outside lawn area, setting up personal camp chairs, binoculars, and home telescopes if you have them. At the very end of this course, there will be a course completion certificate issued, which you can use to go to a bookstore and look official and put on your wall next to your hunting license or something like that. So basically, come to the meetings, be prepared to learn new things, and don't be afraid to ask questions, but hold them till the end, because with 70 people in here, I couldn't control all of it. We need to pass a mic around to really make it clear what's going on. This is our roadmap. Tonight is our introductory section. And following that, next week, we will have Mehmet Unsoy, who's hiding in the back with his lovely wife. He will be doing the session on observing with the naked eye. There is so much you can see if you just know where to look in the night sky. Following that, we're going to talk about observing tools. By that we mean binoculars, telescopes. Steve Barr will be presenting module number 3. By the way, I'll be here for all of the sessions to be kind of the master of ceremonies and whatnot. Number 4 will be the outdoor lab session held at Chamberlain Observatory. Following that, we will have a session that will require you to have either a laptop or an iPad. And I've mentioned in the welcome letter what you should download in preparation for that. Session number 6 will be on basic astrophotography, which is, the simple photographing of stars, constellations, things like that. The final session will be an abbreviated description of deep sky astrophotography. Now, when we were preparing this, I had a bunch of people say, "What the heck are you going to throw astrophotography at people that are just trying to learn where to find stuff in the night sky?" There is a very simple answer. Some of the objects that are out there, the only way you can see them is with a camera. And you'll find that out. A really good example, the Milky Way. You really can't see the Milky Way very much other than a gray streak over the clouds, Deep sky astrophotography basically is a transition where you now are using some very expensive equipment that basically includes a tracking mount, which is a mount that adjusts itself to hold an object in the telescope view while the Earth rotates. So it's running counter to the Earth's rotation, so it stays on focus. Kinds of astronomical objects we're going to talk about in this course. Stars, obviously, one of my favorite subjects. We're going to talk about galaxies and constellations, which are collections of stars. Globular clusters, open clusters, these are basically irregular groupings of stars. Some of these are very, very old, and they've been around, and they're pretty interesting once you get into them. Nebulae. Nebulae are gaseous clouds of hydrogen, helium, and some other rare gases that are typically found in star-forming regions. Now, there is one nebula that you can almost see with the naked eye, Orion. The Orion Nebula, you can just barely make out that there's something funny and it's got a little bit of purple in it. When you look at it, I think with your naked eye, it looks like a bat, like a miniature bat that's a little red. We're going to talk a little bit about planets. These are rocky or gaseous bodies. Rocky planets would be like Earth, Venus, Mars. There are also gaseous bodies. Jupiter, Saturn. They call these like the great gas clouds. What they are is massively large, but they're gaseous. Comets. These are rocky or gaseous deep space objects that appear every now and then. Okay. So first question, what constitutes an observable astronomical object? Any ideas? What makes it observable? Brightness? What else?
You can see it.
Well, yeah, you can see it. Brilliance, the light part is really important, but how about the size? We're going to talk about both of these. So it's size and brightness, and it's usually some combination of both. Another thing that really affects the location of the observer. There are certain things we can see very easily. There are certain things that you won't be able to see because we're in the northern hemisphere. How about the calendar date and the time of night? One of the things we're going to talk about is the fact that because the Earth is rotating about 15 degrees every hour, certain things come into view in the night sky, and later on they disappear because they go above and then below the horizon line. Okay, go for it. There we go. The other consideration that's really important for an observable object, you got to be in a dark place. If I wanted to go observe the night sky in the middle of Central Park in New York, it isn't going to work too well. Wouldn't work too well on the Strip in Las Vegas. And the reason, there's too much light pollution. You want to go to some place where it's very, very dark and you see the entire canopy of the night sky. So the first big object, and we'll talk about how to observe it safely and how to photograph it in later sessions. This is an image of the sun with sunspots. This is one during the eclipse of last April 8th I took this down in Arkansas. Both of these this was before the eclipse, this was right in the middle of it. The button clicker isn't clicking. Oh, there we go. The moon is also a huge night object. Gives you the opportunity to study mountains, craters. The moon is just filled with craters. And with a telescope or binoculars, you can see quite a bit of it. This was the super blood moon lunar eclipse of January 2019. I took this up in Mount Falcon Park. Believe it or not, that's a pretty dark sight at night. I think the battery's going in this guy. There we go. The other things that we're going to talk about how to visualize or how to find are planets. This is a shot of Jupiter and the 4 Galilean moons. It's cropped up quite a bit, but you can see the stripes, and the 4 dots are the moons. I did this from my back deck. This is Saturn with the moon Titan. So we're going to talk about how to find that. One of the Messier objects that's pretty easy to find is the Pleiades in the night sky. Sometimes they call it Subaru or the Seven Sisters. It's got multiple names, but took this in December of 2021, and this was enlarged via a telescope. Okay. Astronomical visual classifications. Astronomers characterize things like planets, galaxies, and nebula by a major dimension. And what that is arc minutes, and I'll get into the arc minutes and arc seconds. I will get into exactly how those are defined. The second term is, of course, the visual brightness magnitude. And that's got a scale. All I can say is I have no idea who came up with it. It's pretty weird when you see how the degradations go, but it is logical to some. Stars are only really characterized by their visual brightness magnitude. So dimensions. A circle has obviously 360 degrees. A quarter of a circle is 90 degrees. Half is 180. Each degree can be further divided into minutes. And every minute, another 60 seconds. Geez, that sounds like we're playing around with a clock, right? The apparent dimension that you're looking at, like for a nebula, how wide across it is characterized by the arc length across it, from top to bottom. This is just kind of a very crude image, but what you're doing is you're pretending it's a clock and how many degrees across the thing. And that is how they characterize the size. Now, there's things about that can be a little bit tricky. One is that objects that are close in to an observer on Earth, they obviously look bigger. Something that is, a million light years away could be big, but all you're able to determine how much, the magnitude is by what you see with a telescope measuring, from one side to the other. Here's some examples of major dimensions. The sun, basically, it puts out about 30 arc minutes. That's basically saying when we observe it from the Earth, it's about 30 arc minutes. Now another one, the moon. When there's an eclipse, the moon and the sun are basically 30 arc minutes. Of course, there's a trick involved here. Obviously, this is when the moon is far enough away that it expands more. If it were close in, you wouldn't get a total eclipse. You'd get what they call an annular eclipse. So basically, the dimensions of the moon, it depends on how far away from the Earth it is in its orbit. Some example major dimensions. Andromeda. Andromeda is huge, 178 arc minutes. And if you divide that by 60 minutes per degree, it works out to about 2.97 degrees. Big, really big. It's a big object. Why can't you see it? It's not bright. It's a very, very dim thing. Although it's big, it doesn't have that much, visual the Pleiades, different. 110 arc minutes, which is about 1.8 degrees. You can see it with the naked eye. And the reason is the amount of light it puts out is so much more than Andromeda. Now I'm going to show you the scale which is used if you look up on the internet, what's the visibility of Procyon or Dubhe or something like that. From ancient times, astronomers have attempted to numerically rank and order stellar objects based upon their brightness. Unfortunately, what they've wound up with is a crazy scale. And I didn't invent it. I'm just telling you how they report it. The currently accepted magnitude scale for light runs from -27 to 27. How bright do you think the sun is on that scale? Is it -27 or +27? Nope, just the opposite. The scale has the degradations basically run the fifth root of 100 between individual magnitudes. And like I say, don't blame me, I didn't do it. No. But at any rate, what I want to show you here is the scale. There is a scale, and you can logically see the sun is really, way out there. The moon is less. Jupiter, Vega, the star Vega is about in the middle. So it has a magnitude of 0. Now, the next thing you see down there is what can the human eye see in terms of a bright object in the sky? Turns out the limit, with this scale is about 6.5. Now, what that means is if you are trying to look at a star or a nebula or something like that, and the magnitude is not 6.5, but let's say it's 7.5, you're not going to be able to see it with your naked eye. Adding things like binoculars can raise that, how low you can go. But in planning to look at something in the night sky, you should probably be looking at something that's, well above 6.5. Be easier to spot. And some of these bright stars like Vega and things like that, they're excellent topics to start off with in trying to observe. I'm going to point out my co-instructor Mehmet there is going to cover this more in the second module next week. But there's kind of a limit on what you can see without aid. So some examples of the visual brightness magnitude. Andromeda, which I told you is huge. I mean, really big out there. The visual magnitude is 3.4. The Pleiades cluster is about 110 arc minutes. The visual magnitude is 1.6. So it is significantly brighter. This is basically why the Pleiades are more visible than Andromeda. So examples of brightness versus dimension. I printed out for everybody's availability a spreadsheet that lists the 110 plus Messier objects. And if we look at, where's the light on? We'll use the other light. Yeah, for those that haven't been in here longer, Charles Messier was a French astronomer, and he was hunting for comets. This was occurring in the time where there was like a transition occurring between astrology and astronomy. There were a lot of people that believed comets were an omen of bad luck. And therefore, he was running around at night, believe it or not, in downtown Paris. He set up a telescope in a building called Le Chatelier. Anybody been to Paris and seen it? Yeah. There's a turret on it. And in the 1700s, Paris was not the city of lights. It was dark. People went around, I guess, with candles. There's no electricity, no gas lights, no nothing. But basically, he was out hunting for comets. The Messier list is basically a list of things. I looked at them, but they're not comets. But everybody uses it as kind of a starting point to go out and look at things in the night sky. What I want to show you here is they've got the visual brightness magnitude, and here's your major dimension. I've also got in here how many light years away they are. So one of the things you see here is like the Crab Nebula. This is a remnant of a supernova that occurred in 1054 AD. It was seen by the Chinese and a lot of other people, and what the remnant of it is the Crab Nebula. There are others in here. You can see the visual brightness, and here are the major dimensions. So you can see some of these are actually fairly large number of arc minutes. Lagoon Nebula, you can see it. You can see where it is. You can't see it like a telescope, but you can physically see it in the Milky Way. And if I had one of my pictures of the Milky Way, like I'm trying to get rid of from my garage, there's an arm that actually points right at the Lagoon Nebula. And you can see it, and look at its magnitude is 6, so it's better than 6.5. Okay. Location of the observer. I mentioned it really helps to be in a dark place like the city of Paris in the 1700s. But if you can't afford that, one of the things we learn is from the northern hemisphere, stars such as Polaris, Deneb, Dubhe, they are readily observable pretty much all year long. What you can't observe are stars, nebula, and galaxies that are in the southern hemisphere. And I brought my little teaching aid with me. Imagine this is the Earth. I'll hold it up in the middle here. This is the Earth, and this little hole in my sphere is Denver, Colorado. Now, if I'm in Denver, I sure as can't see the back side of this. And the things that I can see are limited by the horizon. There's a horizon line around there. And that limits what you can physically see. So, if I go to the southern hemisphere, like if I go to South Africa or something like that, or Australia, you can observe things like the Southern Cross, the large Magellanic Clouds. There's a lot of galaxies and nebula that, they're on the south side. You won't be able to see them. You can't see Polaris, though. But what I'm trying to have you visualize, you got a horizon line where you're viewing from. You're going to have things that dip below that horizon line based on the time of the year. That's a picture of a large Magellanic Cloud and the Tarantula Nebula in the middle, or in the top. Okay, observability changes over the year. How many enjoyed the switch over to daylight savings time? Well, I think it's affecting some of the people, look like they're ready to fall asleep on me. And I'm just going to blame it on the daylight savings time, not my lecture skills. But at any rate, observability will change over the year. Why is that? Well, first of all, the Earth is in a rotation around the sun. We all know that. You learned that in grammar school. What I bet you didn't learn was that the Earth has got a tilt. Throughout the time it's rotating around and going around the sun, it's like a top that doesn't wobble back and forth. It's pretty much staying on a constant 23 degrees, 30 minutes, 17 seconds. So there is they call it the obliquity. That won't be on the quiz though. But basically, obliquity gives us the seasons, not daylight savings time, but it gives us the seasons. But one of the things it does is it limits portions of the sky that you can and cannot see. As an example, you will probably hear the phrase a winter constellation or a summer constellation. And if you're a fanatic about shooting the Milky Way, which is like me, there's a period that we look for, the sweet spot, and that's when the galactic center of the Milky Way is above the horizon. That's typically May through September. But basically, obliquity limits what you can see of some objects near the horizon. Observability over one night. The Earth is rotating around the north celestial pole 360 degrees every 24 hours. That's our basis of what 24 hours means. That basically means the rotation of the Earth is going to shift 15 degrees every hour, which works out to be 1 full degree every 4 minutes. Now, we don't feel it. Even when you're coming out of a bar at 1 a.m., you don't feel, but you don't feel the Earth rotation, but it's there. Where you really see it is you take a picture or you put a camera and point it up in the sky, and you see things like this. This was a picture I took out at Fisher Towers in Utah, and you can see that's sort of where the North Pole is, but everything is rotating around that. And this is an equivalent picture. This was taken at Balanced Rock and Arches National Park. Again, the same thing. Put a camera, look at the sky, it's rotating. But the deal is, along the horizon, you've got some things that are kind of appearing and other things that are rotating away and disappearing at the same time. So the observability changes during the night while you're out trying to observe. Now, my suggestion to people that are trying to get into observing is go for the northern stars. They may rotate, but they're not going to be rising and sinking. For some of the fanatics that want to go out and photograph all of the Messier objects, guess what? You may have something that doesn't rise until 1 a.m. and then it sets at 6 a.m. So it's like, I'm going to let the teenagers deal with that one. So modules 5, 6, and 7 in our course will cover how you go about planning to deal with these kinds of effects. Particularly stellarium and telescopius. Those pieces of software will help you understand what you can, decide to go out and look at. Now, some people say, sometimes I really enjoy just getting a deck chair and a comfortable camp chair and looking up at the sky and just seeing what's there. That's cool too. We encourage all of that, by the way. At some point, you're going to say, there's some interesting things I've read about such and such star, and I'd like to go find it in the night sky. And we're going to help you, systematically plan exactly how to go do that. So I'm going to give you a summary of the key concepts we've talked about tonight. Observability of a star considers the location of the observer. Are you in the northern or southern hemisphere? Visual brightness magnitude. This affects stars, planets, nebulae, and galaxies. If it's too dark, you're not going to be able to see it so easily with the naked eye. You may need some technique like with a camera to capture a time image. The major dimensions of what you're trying to look at. You're going to have a hard time trying to spot Pluto. You may have a hard time spotting Neptune. They're out there, but their dimensions, because they are that far out, are going to be relatively quite small. Obliquity, which I talked about. Basically, objects that are near the horizon may not be visible at all times. And we can use tools like stellarium to predict exactly what's the best time to go out and, like, if you wanted to look at something that was right on the horizon. There's a lot of nebula that, they appear and then they disappear with the rotation of the Earth. And sometimes they won't appear at all until winter versus summer skies. The degree above the horizon, this impacts the rise time and the set time of many of the objects. If you are trying to just go out and take have a nice look for northern stars, northern constellations. Ursa Major, Ursa Minor, the Pleiades, Orion. Orion's been beautiful the last few weeks. Now, prep work for Module 2. Before you come back next week, Module 2 deals with what you can see with the naked eye. This is basically what are the objects you can view that are above 6.5 on that magnitude scale. I'd like you to use some internet resources considering visual brightness, magnitude, and dimensions. Identify 3 northern hemisphere stars that should be visible. And you could do this, like a Wikipedia search or something like that, but come up with a few that would be interesting targets. By the way, we may want to use these when you get to the our field laboratory in Module 4. I'd like you to look for 2 northern hemisphere galaxies that should be visible. Orion, hint, hint. Pleiades, hint, hint. That concludes what I was what I'm presenting for tonight's intro to the subject. Do you want to do a nature call break?
Can you repeat those, please? Identify.
Yeah.
Go back to that. Yeah, that'd be great.
If you download the course PDF version. All of that is in there.
Okay.
So what I'm asking you to do is find something that will be visible, and you have a good shot of seeing it this spring. Not a rough task, but. So we'll take a break to use the washroom.
Okay, if everybody's back, ready for questions and answers, right? Or at least questions.
I'm ready, yeah.
So if you have a question, raise your hand and I'll bring the microphone over to you.
Right over there. I like what he said, that we'll have questions and maybe answers.
Okay, so there were some hands over here.
Yeah,
I had a question regarding the obliquity.
yeah,
You said that gives us seasons.
yes.
How is that? If you have any idea.
Let me pull up that slide. I'll show you. That's a very good question. So the question was, why does obliquity give us the seasons? Really good question. Basically, the sun is shining on this part of the earth while it's tilted over here. Okay? If you notice, this part in the northern part doesn't get much sun. This would be like why I used to go to Sweden quite a bit on work, and the sun would rise in Stockholm at 9 in the morning and would set about 2:30 to 3 in the afternoon. And the reason is, although the earth is spinning, this upper area doesn't get much sun. Now, if we get over to here, that same part of the northern hemisphere, you see it up there? It's getting sunlight. Now, you're going to get sunlight around the equator all the time, but in the northern hemisphere, the northern parts, spring and summer and winter, different seasons. But it's all because the earth, while it is spinning, maintains this constant angle. Yeah. Pardon?
Even if the earth was not like this, it would still, like, specific portions.
No, it wouldn't. The whole earth would get the same amount of sun all the time. You wouldn't have, what do you call it, the white nights, like if you're in Finland in the summertime. You got a period, because this angle is tilted towards the sun and it's rotating. They have daylight up there. God, I remember playing golf up there in the middle of the night. Didn't improve my game, but if there was no obliquity, the earth would continuously have the same amount of light all the time. Does that help? Sort of. Other questions? The back there?
Yes, when you were saying that in the summer, there in that part of the season when it's in the summer. So would you say when we think of the Earth and it's 360 degrees, would you say now the Earth has 270 degrees of daylight and the other half has much less, or is it still split?
I couldn't give you a number. I'm sorry, but the idea is that because of this obliquity, it affects what we can see when we go out to observe stars. The stuff that you want to look at that's in the far north here, you're going to be able to see that all year long. Like you can find Polaris all the time. But stars that are, farther south, you're going to have a rise and set of various stars and constellations and things like that. Have I exhausted all the questions in this inquisitive audience? I see another hand.
Okay.
Okay, I have one comment and a question. As far as you were talking about the northern latitudes and the longer days during the summer, shorter days in the winter,
Yeah,
it's my understanding that the Arctic Circle is the latitude where the sun does not go below the horizon for a period of time in the summer.
I believe that
And it
is,
does not rise above the horizon
Yeah.
for a certain number of days.
I
in the
believe you are
winter.
correct. I am not 100%, but I think that's the
Think
definition.
so. And the Antarctic Circle is the opposite. It's
Yes,
winter and summer. But I mean, that's what I understood the definition of
yeah.
those points were. Okay, so that's a comment. My question was, and I may have be hearing things, but you were talking about a way to tell which objects or bodies would be visible at a certain point of time. And I thought you said something called Starlarium.
Yes.
Is that the name of it? What is that? A chart? Is it a
Stellarium is it's an app on an iPad, and it's a downloadable program on a laptop. It's free. I guess on the iPad version you can get an enhanced version for $18 more, but the free one works just fine, in all honesty. But on the welcome letter to this program, it lists where to download those for free. Stellarium came from France, and one of the things I've noticed is they have like a bogus horizon line, which looks like French farms around you, but it's an incredibly powerful tool. It simulates the whole movement of all of the heavens. And we will cover how to use that in Module 5. The key thing is to put in your exact location and the time you want to look at it, and it shows you the night sky, what you'll be able to see. The one thing that I'd say is difficult is it's hard to go out in the field and say, boy, what the heck is that thing up there? You can't do that easily with Stellarium. But what you can do is there's iPhone available apps like Skyview that take the camera on your phone, and it knows where you're at, and you can raise it up and it says, oh, you're looking at Regulus, or you're looking at Procyon. That's a really fun app, and I have put in the welcome notes. Make sure you have it on your phone when you come to our lab session out at Chamberlain in Module 4. Any other questions? Yeah, ma'am?
Sorry, one more question. You made a note about that observability changes during night.
Yes.
Why not during the day? Like, we cannot just see it? That's the reason?
It has to do with the fact that, I think I'll show you on that. I had a picture that kind of shows that. I can back this guy up. If you look at a picture like this is looking at the North Star. Everything is rotating around it. That's what I'm trying to show you in the picture. If I'm looking at a far northern star, it's just going to go like this. On the other hand, if I'm trying to look at a star or a nebula that happens to be near the horizon, it's going to have a period where it rises, and it's going to have a period where it's gone. And again, I'm telling you, we can show that with Stellarium. It's a good question, though, but I mean, do you understand the concept that on the horizon, you're not going to be able to see everything that isn't, right on the far northern end? The other question.
How come the North Pole doesn't move too?
It is. Okay, that raises an interesting point. First of all, they call it the Polaris. The Polaris is not the northern celestial pole. It's off a smidgen. When you go to align a telescope, when they call it polar aligning, you start with the Polaris star, but you have to adjust it because it's not exactly where the North Pole, the celestial pole is.
So it's really just moving around, you just can't quite see it.
You can't see it because it's like a degree, it's a few minutes off. But that's one of the key things that's done when someone's trying to do a very, very detailed, long-term exposure of something that's very faint, and they polar align it with a tracking scope that automatically adjusts the position of the scope to compensate for the motion of the Earth. That's wonderful stuff. It'll cost you $600-700 for the mount, but yeah, lady has a question.
I was wondering if you could just very briefly go over that Messier chart and just what the columns mean.
Yeah, okay.
Some of it is like
I got to sit down. A year ago, I had my knee replaced, and this is the chart you're referring to. Yeah. Okay. The Messier catalog has and I sent that to y'all in an Excel spreadsheet. This first column is the Messier designation of all of these objects. NGC is a different catalog. It's, they call it the new general catalog. I can't remember, but I think new was still a few centuries back. But the Messier catalog has a little over 110 objects in it that were not found to be comets. The NGC catalog, or the New General Catalog, do we got any Star Trek fans in here? What's the designated number of the Starship Enterprise?
1701.
What?
1701.
Yeah, NGC 1701. Guess where that came from? At any rate, this is the corresponding catalog item on the new general catalog, okay? It's showing here the codes in here. GLCL, that means globular cluster. It means it's a thing that doesn't rotate very well. It's just kind of how would you describe it? Like a Jackson Pollock art show. There's a lot of these. OPCL means open cluster. DIFN, this is a diffuse nebula. Remember I mentioned a nebula is a formation of gases like a lot of hydrogen, helium, and stellar dust. Things from past stars that blew up. But all of these, they basically mean what you're looking at. This is the constellation. Tau is Taurus, Aquarius, some of them, Sagittarius, Ophius. They're all located in various things. Now, these two columns here represent the physical location of the actual star. I guess I did not explain that in my talk, so let me sit down and explain it now. All stars, the position of them, are basically fixed in the sky. But the Earth rotates around the sun. The Earth rotates during the day. So how do you know where to find a star? Well, this is how they do it. The observatory in Greenwich, England, sits on a 0 degree line, okay? where you see right ascension here, that is the difference in hours and minutes away from something you would see at midday on the spring equinox. All these positions, the right ascension and the declination, are all fixed based on that. But if it's on the opposite side of the world, you're going to see numbers that go up to 24 here. So that's how they're pegging the location in the sky. The declination, this is degrees and minutes. When you see something that is 22 degrees, it means it's like 22 degrees up. On the other hand, if you see this guy 43 down, that means it's below the equator. So if you are planning in your night sky to go out and do a Messier marathon, good luck with that one. You would have to be somewhere pretty far south to see that. You won't see it from Denver. Sorry. There are ways to get around that, like go take a trip somewhere or buy telescope time at an observatory. But that's basically how this works. Right ascension is the difference in the night sky, or it'll be daytime, but as you go around the globe 24 hours where the thing is, and this is the elevation. Does that help explain what those two are? When we get to using things like telescopius and stellarium, you know what's nice? It does it automatically. You don't need to know. All you got to be able to do is say, hey, I'd like to go find Procyon. Where will I find it tonight? If you put your exact location, latitude, longitude in, the exact time, it will spit out exactly altitude and elevation to go look for it. But they are all based on knowing these two numbers in this column. And then we got your visual brightness and the major dimensions, how big they are. And there's a lot of them have common names, like the Whirlpool Galaxy is, Messier 101. As a year or two ago, there was a supernova event on M101 and one of the tails of it. There was a lot of chatter in the astronomy-related web pages about it. Turns out there's a Japanese astronomer that apparently spends all his time looking for supernova events. He's recorded. I'm trying to figure out how he does it. He obviously has something automated on a computer that's looking for something that wasn't there the day before, and that's how he apparently gets it. I don't know. Any other questions about that chart?
John, we have a question over here.
Yeah. Ma'am?
Thank you. Not about the chart. Firstly, thank you for doing this. This is fantastic, and I'm super appreciative. So I'll give you a hand on that.
All I will say is you ain't seen nothing yet.
So I fear that I might be jumping the gun because I'm very excited. And prior to our next meeting on Tuesday, I have heard that there is a blood red moon coming up in 2 nights.
Yeah.
And I have been searching on my magic box for where I can go watch it from Denver because I'm not going to be able to travel.
Do you really want to go out that late at night?
It starts at 11:09. That's not that bad. But yes, if I happen to be up and if I happen to be in a position where I can get outside and look at the moon, from where or with whom or how might I do that?
I had a shot. Earlier in the presentation, I had a shot of the last super wolf blood moon eclipse back in, was it 2019? Yeah, I think it was January or late January in 2019. Where's a pretty good spot Do you know where Mount Falcon Park is? I just set my camera and my gear up in the parking lot, and the top side. That's pretty darn dark up there. They don't have cops up there saying, "What are you doing up here?" But that's a pretty good spot because it's wide open. You can drive right up to it. You don't have to walk very far, and it still works. For me, I'm 75, and I'm getting to the point that some of the places I want to trek to take pictures, my body just says, you shouldn't do that anymore. But Mount Falcon Park is not bad.
The corner of 84th and Federal attracts 100 people plus for the 4th of July. And it looks out over the city. And I bet it would look out over the eclipse too.
It depends. I really wish we had a simulation of what it's going to look like, minute by minute. Darn it, Stellarum will show you the darn thing. Yeah, question.
Well, as it happens, today I found a snapshot of a weather forecast for the eclipse, and it looks like the Denver, probably the Front Range, is in a good location as far as cloud cover. If you go too far east or too far west, it doesn't look so good.
Yeah.
So you might want to, if you really want to go out,
Check
just
the weather.
for that point, just to see that, then you might want to check the weather forecast first.
Yeah, it's about an hour drive up 285 and then
Mount Falcon should be fine.
Yeah,
Perfect.
go for it. Anybody else? Well, oh yeah, question.
Do you think Pluto should have been demoted to? I grew up with 9 planets.
I know, and they named the dog in Walt Disney Pluto. It's really kind of crazy. The criteria, what do they call it? The International Astronomical Union, IAU, sounds like a union, but labor union. But at any rate, they had a criteria that said that to be a planet, you had to be pretty much coplanar with the sun, and that you had, over time, swept out the path of your orbit so that you were not bonking into things. And the problem with Pluto is the orbit is not coplanar with all the rest of the stuff. And, I don't know why. It's an interesting object. It's got moons. It's been seen by some of the, the satellites that have been out there, but, it is what it is. I couldn't argue with the Messier tables either, what he did, but, all our chemistry, if you look at the periodic table of the elements, we go Uranus or uranium, neptunium, plutonium, they're all in the same order of the planets, and then they kicked it out of the solar system. I don't know. With that, I think we're ready to close.
Thank you, John. Appreciate your efforts here. And